All right. So let's So it is 2025, September 27th, approximately 10:39 a.m. Going on to exercise 13. Exercise 13, which is, it's not a lot in the question there, at least from what I gather. It just says find the kernel of the left regular action. Words can encapsulate a lot. So the left regular action, that's G cross G maps to G, that being G comma A goes to G dot A, which goes to GA. An element G is in the kernel, if and only if it fixes every A within big G, I mean to say. That is little g A is equal to A for all A. By cancellation or uniqueness of identity, this forces G to equal 1. So let's take a look at that more rigorously though. So for our step 1 here, action and kernel, let's let G cross G, let's just define this as a map, right? G cross G maps to G, and more explicitly, open parentheses, G comma A, close parentheses, maps to G dot A, which is equal to GA. Let's let that be the left regular action. Now, its kernel is such that the kernel is equal to the set containing G within big G such that little g times A is equal to A for all A within big G, which consequently is equal to the set containing G inside big G such that GA is equal to A for all A within G. Right? So we have our setup for the step 1. Now let's try and get more precisely what the kernel could be outside of just this set abstraction, though a lot of it is just merely set abstraction. That's like almost all of math is set abstraction. So step 2, we want to identify the kernel, because I can tell you what something is definitionally stating, right? It's like, but that's one thing, and actually showing you what that thing is concretely in a more concrete case is another thing. So in this case, let's say if G happens to be an element of the kernel, then in particular, GA is equal to A, with A being equal to 1, gives G dot 1 is equal to 1. That is, G is equal to 1. Right? That follows directly from what we established earlier. So conversely, G equals 1, it clearly fixes g equals 1 fixes every a, right? So the kernel is equal to 1. It's another point against it, but it's more so just like, can we say that, no, it fixes every a, so it alone would be contained within the kernel in this case. And we can't really say it's anything else because of the way in which the regular action, the left regular action behaves. I don't know. What is it? Structurally implies, right? So yeah, and so, well, fixes every a, it's unique, right? The left, it's trivial, regular action is faithful. Which isn't what we were looking for, we were just told to find it, but yeah, doesn't hurt to add. Now, to conclude, what do we have? Well, the kernel of the left regular action is equal to the set containing 1, and hence the action itself is faithful. But I'll just add that as a parenthetical. Okay, so that's it for exercise 13. Let's move on to exercise 14. Gotta stand. Yeah, okay. So, for exercise 14, we have let G be a group and let A equal G, big A equal G. Show that if G is non-abelian, then the maps defined by G dot A is equal to AG, that is to say, well, with G and A being contained within G. So defined by that, do not satisfy the axioms of a left group action of G on itself. That's what we want to be able to say. So, a left action must satisfy G sub 1 dot open parentheses G sub 2 dot A close parentheses is equal to open parentheses G sub 1 G sub 2 close parentheses dot A, with the rule that G dot A is equal to AG. That is to say, right multiplication by G. Left-hand side becomes A G sub 2, G sub 1, while the right-hand side is A open parentheses, G sub 1, G sub 2, close parentheses. These agree for all precisely, for all A precisely when G sub 1 and G sub 2 commute. Now, if G is not abelian, we can pick G sub 1, G sub 2, with G sub 1, G sub 2 not equal to G sub 2, G sub 1, and the axiom fails. So that's the intuition. Now let's get into looking at this a bit more rigorously, right? And see what we can make of it. So to start a claim, we want to show if G is non-abelian, the map open parentheses G comma A close parentheses to G dot A is equal to AG does not define a left action. So let's see if we can verify that. We want to, so as I mentioned a bit earlier, as I hinted at within the intuition, verification of the compatibility axiom fails. Stand up, take a look. Okay, so let's choose G sub 1, G sub 2, contained within big G with G sub 1, G sub 1, G sub 2, not equal to G sub 2, G sub 1. Because it's not abelian, we can say that. So for arbitrary, well, actually, let me just erase this and then I'll write more. Okay. So for arbitrary A within G, we have that G sub 1 dot open parentheses G sub 2 dot A close parentheses is equal to G sub 1 dot open parentheses A G sub 2 close parentheses, which is equal to open parentheses A G sub 2 close parentheses G sub 1, which is equal to A open parentheses G sub 2 G sub 1 close parentheses open parentheses G sub 1 G sub 2 dot A is equal to A open parentheses A sub 1, I mean G sub 1 G sub 1 G sub 2. So the action axiom here, the action axiom G sub 1 dot open parentheses G sub 2 dot A close parentheses equal to open parentheses G sub 1 G sub 2 close parentheses dot A would force A open parentheses G sub 2 G sub 1 equal to A open parentheses G sub 1 G sub 2 close parentheses for all A, and by cancellation G sub 2 G sub 1 equals G sub 1 G sub 2, which is a contradiction. So I just kind of, yeah, there we go. So I noticed there's a glint there. Can't really do much about that, but okay. Even if I rearrange that the lights are fixed such that I didn't have a covering in any such way, there would be a glitch somewhere and it would interrupt the way it looks. Over here, I keep it a bit minimal. Though maybe if I scoot it up a little bit, I can kind of take care of that. It's not easy to write there. Okay, just gonna deal with the glint. Okay, so So the compatibility axiom fails. So this is not a left action when G is non-abelian. And whenever G is abelian, A open parentheses G sub 2 G sub 1 close parentheses is equal to A open parentheses G sub 1 G sub 2 close parentheses. So that holds, so the rule does define a left action whenever G is abelian. So to conclude, for non-abelian G, the map open parentheses G comma A close parentheses to AG does not satisfy the left action axioms. All right, on to exercise 15. So for exercise 15, we have let G be any group and let A be equal to G. Show that the maps G dot A is equal to AG to the negative 1, and of course G and A being elements of BG, show that these maps satisfy, show that these maps here satisfy the axioms of a left group action. Okay? So how do I say this? It said any, right? Not just abelian. But at the same time, let me think about this. Let me think. Okay, so intuitively, it's like, well, a left action needs G sub 1 dot open parentheses G sub 2 dot A close parentheses, which is equal to open parentheses G sub 1 G sub 2 close parentheses dot A, with the rule that G dot A is equal to A G inverse. We get G sub 1 dot open parentheses G sub 2 dot A close parentheses is equal to G sub 1 dot open parentheses A G sub 2 to the negative 1 close parentheses, which is equal to open parentheses A G sub 2 to the negative 1 close parentheses G sub 1 to the negative 1, which is equal to A open parentheses G sub 2 to the negative 1 G sub 1 to the negative 1 close parentheses, which is equal to A open parentheses G sub 1 G sub 2 close parentheses, all of that to the negative 1, which is equal to open parentheses G sub 1 G sub 2 close parentheses dot A. So the order reversal from inverses is exactly what fixes the associativity constraint that failed in exercise 14. So let's go ahead and show that with a bit more rigor and pop to it. Rigor and pop. Okay. So what can I say? What can I do? Let's say, okay, what can I claim? So claim, we want to show, right? So we want to show the map, open parentheses, G, comma, A, close parentheses, to G dot A, which is equal to A G inverse, defines left action. A left action of G, of big G on big G. So let's just start with the identity axiom. So for any G, for any A within big G, we have 1 dot A is equal to A1, the inverse of 1, so 1 to the negative 1, which is equal to A1, which is equal to A. So we have the identity axiom. Now let's look at the compatibility axiom, which is the main issue for the previous problem. So, well, I'm going to need more room. So, okay, for any G sub 1, G sub 2, A contained within G, elements of G, we have G sub 1 dot open parentheses G sub 2 dot A close parentheses is equal to G sub 1 dot open parentheses A G sub 2 to the negative 1 close parentheses. I know it's probably better for me to say G sub 2 inverse, but G sub 2 to the negative 1 is just a whole lot easier to say, and you already know what I mean anyway. So, but back on track, this is equal to open parentheses, well, no. It's equal to, yes, it's equal to open parentheses A G sub 2 to the negative 1, close parentheses G sub 1 to the negative 1, which is equal to A open parentheses G sub 2 to the negative 1, G sub 1 to the negative 1, close parentheses, which is equal to A open parentheses G sub 1, G sub 2, close parentheses to the negative 1, which is equal to open parentheses G sub 1, G sub 2, close parentheses, dot A. So both axioms hold. Ergo, this is a left action. So don't ever show it to anybody from Eastern Europe. Okay, so conceptually this is the right regular action twisted by inversion, right? So G dot A is equal to A G inverse is the same as right multiplication by G inverse. So, and inversion turns product order around in this case, which is why compatibility works for all groups, abelian or not. So what can we say? So let's conclude something here. So to conclude, for any group, G, the map, open parentheses, G, comma, A to A, G inverse is a valid left action of G, of big G on big G. So let's ax by right inverse. The inverse flips order, restoring the left cancellation law. So we're good to go for exercise 15. Let's move on to exercise 16. All right. So for exercise 16, we have let G be any group and let A equal G. We want to show that the maps this looks, so let me see, how does this differ from 15? Okay, goodness, yeah. Show that the maps G dot A is equal to GA G inverse, where G and A are elements of G, satisfy the axioms of a, no, I'm not going to put parentheses, of a left group action of G on itself and parenthetical, this action is called conjugation. So conjugation is transporting, it's like, it's, bear with me here. Conjugation is transporting A into G's coordinate frame, let's say, and back. The inverse on the right restores the order so that G sub 1 dot open parentheses G sub 2 dot A close parentheses is equal to G sub 1 open parentheses G sub 2 A G sub 2 to the negative 1 close parentheses G sub 1 to the negative 1. And this is equal to open parentheses G sub 1 G sub 2 close parentheses A open parentheses G sub 1 G sub 2 close parentheses to the negative 1, which is equal to open parentheses G sub 1 G sub 2 close parentheses dot A. And identity is immediate because, 1 A 1 to the negative 1, that's equal to A. So let's take a look at that a bit more rigorously. See what's what. Okay, so for the claim here, the map open parentheses G comma A to G dot A is equal to is equal to G A G to the negative 1 defines a left action of G, of big G on big G. So that's our claim. Now let's look at the identity axiom, see if that holds for this case. It's more so that this sticks to the axiom more so than the axiom itself holds, because an axiom is an axiom. It's just, that's a tautology, right? But it's like, that's the thing that's believed in order for the thing to work. So for any element A for any element A of G, element A in G, 1 dot A is equal to 1A, 1 to the negative 1, which is equal to A. So the identity axiom holds. Now let's get to the more interesting part, which is the compatibility axiom. So for the compatibility axiom, let me speak a lot faster than I can write, so it's a bit of a pain sometimes, but you know what? It slows me down enough to force me to think about things a bit more slowly, so that's kind of nice. So for any G sub 1, G sub 2, G, 3, just keep going. A contained as elements within G, we have that G sub 1 dot open parentheses G sub 2 dot A close parentheses is equal to G sub 1 open parentheses G sub 2 A G sub 2 to the negative 1 close parentheses G sub 1 to the negative 1. And that this is in fact equal to open parentheses G sub 1, G sub 2, close parentheses A, open parentheses G sub 1, G sub 2, close parentheses to the negative 1, which is equal to open parentheses G sub 1, G sub 2, close parentheses dot A. So both axioms hold. Both axioms hold. So this is a left action. Once again, keep it away from Eastern Europe. They don't like that sort of thing anymore. It's almost as if living under a communist state. An actual communist state makes you less likely to like communism. And if the only example your opponent can bring up is Yugoslavia, it's because everybody that ever opposed the government in Yugoslavia was executed, and so there's nobody left to comment badly about it. But, you know, that's a different subject. So, for fixed G, the map from A to G, A, G to the negative 1, that's an automorphism of G, an inner automorphism. Stabilizer of A under conjugation is C sub G of A, which is equal to the set containing G, all little g within big G, such that GA is equal to AG, the centralizer. The orbits are the conjugacy class. So that's just a little remark there. I'm going to start adding those just to add more and more context to what we do, because I feel like that's a good thing to do pedagogically speaking. Like just, you know, add a little bit here, a little bit there, so that it's not too overwhelming, but it's just enough. So let's include for any group G, open parentheses G, comma, A, close parentheses, to G, A, G to the negative 1, is a valid left action, which is, this is also known as conjugation, right? So, yeah. So, let's sandwich it, right? Sandwich it such that G, sandwich it, not sandwich, ship your pants somewhere, but, you know, G on the left, G inverse on the right, associativity does the rest, right? So, but, you know, that's our concluding statement. Let's move on to exercise 17. So, let's see here, what do I need to do? Right. So for exercise 17, let G be a group, and let G act on itself by conjugation, which is what we just showed there previously. X maps to G, X, G inverse for fixed little g within as an element within G. So this has three parts. One is to prove that conjugation by G yeah, so that conjugation by G is an automorphism of G. Part 2, to deduce that X and G inverse have the same order for all X within G. And part 3, for any subset A of G, prove, oh no. I don't think I have enough space for this. So keep that in mind. I'm gonna need more board space. So part 3 is to say that, prove that for any subset, well, A of G, we have to prove that the order of A is equal to the order of G inverse, where G inverse is equal to the set containing G inverse such that little a is contained within A. Okay? So intuitively, conjugation by G is just renaming the coordinates of G, multiplied by G on the left and undo it on the right, because G x of 1, x of 2, G inverse is equal to open parentheses G x of 1, G to the negative 1, close parentheses, open parentheses, G x of 2, G inverse, close parentheses. It respects the group law because x maps to G to the negative 1, x, G is its inverse. It's bijection. Automorphisms preserve orders and bijections preserve cardinalities. So the deductions follow immediately. Right, so, well, relatively speaking, immediately. Like, not like, you know, like faster than a speeding bullet or anything like that. It's like, we'll see, right? I mean, it's like, why have rigor if you're going to say such things? But respect the colloquial nature of our language, I guess is a way of saying it. It helps encapsulate things really fast. And perhaps it's also like, if you just say something immediately, it's like you say it enough, it becomes true. No, but it's like, no. That's dark. Okay, let's not. What I mean to say is, it's like, why say immediately? Why say obviously? Why say all of these things? Well, it's like, presumably it's because a reasonable explanation, it's because like the person that's looking at that sees that and says, oh, okay, I've already encapsulated everything. I've already practiced everything to the point which I can say it's obvious, but you can't say it's obvious yet. So, but it's also like, if you're going to start and do something, it's like you sort of have that sort of wish-fulfilling thing that you say, follows immediately. Let me show you how it goes in a way that's easy and intuitive and connects point A to point B in a way in which it's deserving of the word immediately, right? So, but, you know, it's just common parlance. So, but getting more back to the subject at hand, let's fix G with little g as an element of 6. No, as an element of big G. And let's define phi of little g to be the map from big G to big G by phi of little g of x is equal to little g x little g to the negative 1. Okay? So for part one, what do we want to do? We want to show that phi of b sub g is an automorphism. Right? Automorphism, more than meets the eye. Okay, more than meets the eye. So for x sub 1, x sub 2 contained within G, phi sub G of x sub 1, x sub 2 is equal to G of x sub 1, x sub 2, sorry, not of. In this case, it's parenthetical, so, well, not parenthetical in the usual sense, but parenthetical in the case that it literally uses parentheses. So G, open parentheses, x sub 1, x sub 2, close parentheses, G to the negative 1. That's what that's equal to, which is equal to, open parentheses, G, x sub 1, G to the negative 1, close parentheses, open parentheses, G, x sub 2, G sub 1, G to the negative 1, close parentheses, which is equal to phi of sub G of x sub 1, and then phi sub G of x sub 2, okay? So we can at the least say that phi sub G is a homomorphism. Now let's see if it's bijective. After I erase this. So we have inverse phi sub G to the negative 1. And what does this mean? Well, phi sub G to the negative 1 of phi of G of x, what's that equal to? Well, that's equal to G to the negative 1, open parentheses, G, x, G to the negative 1, close parentheses, G, which is equal to x, and phi sub G of phi of G to the negative 1 of x. Well, what's that equal to? That's equal to x, right? So it's bijective. It's bijective. It's phi. It's bijective. So it's bijective with regards because we have that inverse. Because we have that inverse and because of what we showed there. So, showed there more explicitly with each of these steps. So, can we then say, knowing that this is in fact a map from big G to big G, well, we can say, okay, so phi sub G is an automorphism, in this case, an inner automorphism. Right? So now let's go on to part 2. Look at that more rigorously. So for part 2, I want to show that orders are preserved. Orders are preserved. So let's let x be an element of G and n be greater than or equal to 1. Well, then phi sub G of x, take that to the power n, well, that's equal to open parentheses G, x, G to the negative 1, close parentheses to the n, and that is equal to G, x to the n, G to the negative 1, which is equal to phi of sub g of x to the n. So phi sub g of x has order n if and only if x to the n is equal to 1. That is to say, therefore, order of phi sub g of x, what is that equal to? It's equal to the order of x, right? So there we have our order preservation. Which is interesting. It's an interesting way to think about it, right? Like bijections preserving cardinalities and automorphisms preserving the orders themselves. So that's a good way to think about it. Now let's move on to, that's supposed to be an x, not a lambda. There we go. Let's move on to the next part, which is part 3. So for part 3, we want to show that conjugation preserves subset sizes. Right, so the restriction of phi sub g on with a here, such that a maps to g to the negative 1. Well, that's a bijection. So this is a bijection. So let me put a note here. Inverse phi g to the negative 1 for g to the negative 1. So it's accounted for with the inverse. So the order of a is equal to the order of g inverse, okay? So that holds. All right. So we have our 3 parts there accounted for. Now let's see what we can conclude. So conjugation x to g to the negative 1 is an automorphism. It preserves orders and subset cardinalities. So conjugation is not just, it's not just relabeling. So it's like g to the negative 1, it has the same structure. Well, no, sorry. Conjugation is in a lot of ways just relabeling, but with that comes consequences. So it's like g to the negative 1, it's like that has same structure, same orders, same sizes, right? So that's the power of an automorphism. That's the power of the Home Depot right there. But yeah, so that's pretty cool, right? Now let's move on to exercise 18. So exercise 18 says let H be a group acting on a set A. And define a relation tilde on A by little a, that's supposed to be a little a, by little a tilde B if and only if there exists H such that, little h within H such that little a is equal to little h dot b. So we have to prove that tilde is an equivalence relation. So for each, that is for each x within big A, the equivalence class of x under tilde is called the orbit of x. The orbits under the action of H, partition A. Okay. Now it's kind of hard to make out that I wrote that, but you heard what I said. So, but anyway, intuitively, being in the same orbit means reachable by the action of some group element. So, identity gives reflexivity, inverses give symmetry, closure, or product in this case gives transitivity. So, the group axioms map exactly onto the equivalence axioms, right? So, let's take a look at that more rigorously. All right, take a pause, get up, walk a little bit. Okay, we're not too far off schedule. All right, now, so let's verify the three properties, right? Okay, good. Verify the three properties. So for the first bit, reflexive, right? Reflexive. So for any A, then A is equal to 1 dot A. So reflexive, so that for any little a within big A, A is equal to 1 dot A, okay? So we have A tilde A, so it's reflexive. Fair enough. Okay, how about symmetric? If A tilde B, then A is equal to H dot B for some little h contained within big H. Now, since little h inverse is contained within H, we have B is equal to H to the negative 1 dot A. So B tilde A, we have symmetry. Okay, now let's move on to transitivity. See if this thing is transitive. No, cissative. Oh, that's a terrible joke. Okay. I like it though. So, if A tilde B and B tilde C, then A is equal to H sub 1 dot B, and B is equal to H sub 2 dot C for some H sub 1, oops, almost forgot about H sub 2, and H sub 2 being elements in H, then A is equal to H sub 1 dot open parentheses H sub 2 dot C close parentheses, which is equal to open parentheses H sub 1 H sub 2 close parentheses dot C. So A tilde C. There we go. We have the three properties in a row. Now, what furthermore can we say? Well, so tilde is an equivalence relation. What's interesting is this is a partition by orbits. So the equivalence classes of tilde are exactly the orbits H dot X, which equal the set containing little h dot X such that little h is within H. So they are pairwise disjoint, and their union, in fact, is A. So to conclude, let's conclude. Goodness, I can't even draw conclude right. That's not cool. Same orbit. Is an equivalence relation. So the orbits partition A. So identity implies that it's reflexive, inverses imply that it's symmetric, products imply that it's transitive. So we're good to go for exercise 18. All right, let's see about this. I think I'll leave it there for now. We'll pick up with the rest of the exercises in the next one. Yeah, that's pretty much it for now. Bye-bye.